All right, good morning, ladies and gentlemen. So now it's almost the end of first half of the semester, and we're in the middle of the course. And now, before going for the break, we will accomplish some work. Namely, we will quantize classical fields. We will quantize them all because, as we have learned, any classical field can be seen as a collection of oscillators, and we can quantize an oscillator. Right. So in the beginning of the lecture, I will explicitly do it step by step. And then we can discuss something interesting. We will do it for our model of string. We will do it for electromagnetic field in very same fashion. Good, we will talk a bit about field. And the second half of the lecture will be devoted to some, I would say, fancy concepts which arise, which are simple consequences of the quantization, which we have performed. It will be about 0-point energy of the system of oscillators. It will be about uncertainty relations for the fields. It will be about vacuum fluctuations of these fields. All this will become kind of straightforward after the quantization. So first half of the lecture is quantization itself. Second, applications to the subjects I have listed. Fine, sir, as usual, questions to the charts, and I will be delighted to react on them. Let me just take a single oscillator, harmonic oscillator. As for realization, I could take a particle in a parabolic potential. It doesn't matter because we have already reduced any field in a form of oscillators like this. Okay. At the moment, we are in classics, and we have a classical Hamiltonian, which has p squared, which has q squared, parabolic potential, parabolic kinetic energy. What do we do classically? From this Hamiltonian, we extract equations which these quantities do obey, evolution equations. Right, now let me, well, we know how to write Schrödinger equation for oscillator. That we also could do, but let us do it a little bit differently. Let me quantize it in perhaps some time-saving manner, which will also give us some immediate connection to things we know, to creation and annihilation operators. Good, sir, I'm going to quantize it. I want to make a quantum Hamiltonian out of that. Well, what do I have to do? This is to promote these classical values to operators. Well, that I did. I just put hats above these quantities. But that is not informative. I have to add something. And what I'm going to add is the commutation rule between these operators. Right. I will add commutation rule, and then I will do quantum mechanical equations. Quantum mechanical equations which are obtained by commutating of any operator with Hamiltonian, right? That's why I need commutation relations. And I would like to reproduce equations which are similar to classical equations. So that kind of closes the loop that shows that I did everything correctly. And there is a correspondence between classical mechanics and quantum mechanics. So that's assumption I would call quantization postulate. Fine. So how we do this in a concrete way? Well, as I said, Schrödinger equation, write a Schrödinger equation for this system is a possibility. However, it's a rather complex possibility. The point is that if I write a Schrödinger equation, I will be able to get the solutions in the form of Hermite polynomials, but that look complex. That look complex, almost as symmetrized and symmetrized wave functions we have introduced. Sure, and the suggestion that we better proceed with operators which we already know in the course of quantization trick for the oscillator. So let me define an operator like this. This is not self-conjugated operator, right? It's kind of has a real Hermitian and imaginary anti-Hermitian part. Right, it also contains ugly square roots, but we know that all ugly square roots are for good. Well, and there is a Hermitian conjugated operator coming. Right. We can show it explicitly that with this definition of commutation between momentum and coordinate, these operators obey the following commutation relations. And at this point, we get kind of an idea which owing to your present knowledge might seem trivial for you, but it was really a great discovery for physicists of that time, that these operators are nothing but creation and annihilation operators for bosonic particles. So we can get to a description of oscillator in terms of particles. So an oscillator with a given frequency, h omega, might be presented, might be seen, is correct to see as a level for bosonic particles. What do we do in order to arrive at this? We will write the Hamiltonian in terms of this A, Dega A. And now I can invoke a real name for this. Those are creation and annihilation operators. The Hamiltonian looks like this, and that can be written as number of particles. Number of particles in this oscillator. So the eigenstates of harmonic oscillators, in fact, of oscillator, in fact, differ by number of particles. Right. As any system of particles, there is, as for any system of particles, there is a special state in this situation, a special state, vacuum. Vacuum, it cannot be defined as empty space. Vacuum has a very much precise definition in terms of annihilation apparatus. Namely, this shows that nothing can be annihilated in the vacuum state, right? It leads to senseless wave function. So that is how vacuum is defined. And as we know from our exercises with bosons, with second quantization of bosons, all other states, all other eigenstates of the system can be constructed by applying certain number of creation operators. What is this number? This number just the number of particles. And after that, we normalize the state. We get eigenstate, and eigenenergies are that, which means that particles do not interact. The particles do not interact. How do I see this? The energy, the total energy, is just the sum of individual particle energies. Well, there is also 1/2 0-point energy. We will discuss it in more detail. So I presume no questions are there at this stage, just rewriting of what we know in more explicit terms. Let me just do this job rather automatically for a set of oscillators. And as we see, there's not so much job involved, just more or less repeat all these considerations for many oscillators. Anyway, let me go through the steps. So this is a full Hamiltonian. It involves summation over many independent oscillators. We want to quantize it. We promote them to operators. And then we need to assume something about commutation relations, and this is what we assume. Right, so the only part to think about that commutator of coordinate and momentum exists only for the same oscillator, right? But that's natural because different oscillators are assumed to be independent, right? That's why the corresponding operators, they kind of act in different spaces. And they do commute. Fine. Using these commutation relations, we will arrive at quantum equations, which will correspond to classical ones. So that's how does it go for big set of oscillators, and well, we still remember that any classical field is a large set of oscillators. Good. Again, we treat this system of harmonic oscillators with operator algebra. One could write Schrödinger equation, but in that case, it really becomes too complex. Hamid polynomials for each of these oscillators. So we better do it differently. We better proceed with operators. And again, for each oscillator, we define an individual operator A, which is not equal to its conjugation. One checks commutation relations, and one reproduces the relation for the system of bosons. Fine. So, any system of oscillators, we go to a high level of complexity, but since oscillators are independent, we can do it without any sweat. We rewrite the Hamiltonian in terms of creation and annihilation operators. Here it is. So now it's the sum over levels over oscillator modes. Right, and we'll see that the Hamiltonian can be expressed in terms of particle number in each oscillator. So eigenstates only differ by number of particles in each level K. And in fact, we understand that now we are in Fock space. We are now in Fock space, where each basis vector can be characterized by a set of occupation numbers. There is a vacuum state, of course, with no particles, and now it's defined that for any K, the action of annihilation operator on vacuum is zero, so one cannot annihilate particle at any level. Everything is empty. Fine. All other states we can obtain in this way. Luckily, operators and a Dagger creation operators do commute. So it doesn't matter in which sequence we create the particles. We only care about their total numbers or a particle. Oh, okay, I missed K. A particle with HK is repeated NK times. Right, the function is normalized, and that leads to eigenenergies. Again, we observe that this those are energies for non-interacting particles. The total energy is just a sum of single particle energies. Fine, that was important to understand that any linear theory corresponds to non-interacting bosonic particles. Fine, basically we did everything. Let me kind of, let me call it a summary. So we have started with classical fields, and now we are about to describe its quantum mechanical states. Since field is a large collection of oscillators, the states of the field, quantum mechanical states of a classical field, are the states of the oscillators. Again, case missed for some reasons. What we have just done, we, as I promised, reached the summit. Although it is like, well, sorry, perhaps I'm too fast. So there are some meats, and there at the top, particles is just the same as fields. We have approached it by two roads. First road was starting with particles, where we figure out what are creation and annihilation operators, and after that, the system has become a field. Well, what we just did, we have started with classical particles, and again get to the, we start with classical field, classical oscillators, which is field, and we perform quantization procedure. We understand that the fields are particles, so here we are on the top. Fine. We did it. That was not, that could be a length exercise. I wanted to do it step by step to get a feeling that you could do it yourself. Indeed, somebody has done it first time. But again, I would stress that it was great, perhaps one of the greatest summits which have been conquered by humans. Equivalence of particles and fields. Any questions at this point? At the point of summit? Fine. I presume that everything is clear. So let us move slowly to applications. Let's get to concrete system. First of all, I want to notice something very obvious, that if I keep it in this way, if I keep the description of the field in terms of AK only, I completely miss any physical content, right? And in order to get back to original values, to the quantities which describe this classical field, I need to invoke a field operator. Yes, we have considered those already for particles. And now we need to do this for fields. Let me recall what we did in previous lecture when we started with some arbitrary fields, or here A stands for arbitrary, right? Starting from arbitrary field, we go to oscillators. We introduce what is called normal coordinates, complex coordinates, imaginary real part of this normal coordinates are conjugated sorry, yeah, mutually conjugated generalized momentum and coordinate, right? And that we can quantize. So at each arrow, we got linear relations. Linear relations we can always invert. So what is to do now is to get from creation relation operators back to these quantities, back to these quantities, and finally arrive at operator. So that was classical value. This is now field operator. All right, so just inversion of the formulas which we have already obtained. Right, so that's allows me to automate examples. So let me recall one of the examples we have considered in the previous lecture. That was elastic string, and quantized oscillations of the string are called phonons. Phonons are present in any solid state in any elastic medium. Quantized elastic motion. All right, let us understand what are. We look at oscillators, and we understand that now they represent the particles with a certain momentum related to wave vector, with a certain energy. So here C is the velocity of these particles, the velocity of speed of waves propagating in this string. Fine. Again, repeating what we have already done, finding the relation, using the relation between normal coordinates and field operator field, we find expression for the field operators. Basically, inverting this relation. So here we are. We have quantized quantum expression for displacement of the string as function of coordinate and time. It is made of two operators in each case. Each mode contributes to actual displacement at a given point, given moment of time. Here we are. Again, it's an ugly square root, which is always present in the definition of field operators, which adequately presented. What is what will become relevant in a couple of lectures, and what I would like to mention now, as we see, if you take a number state, a state with definite particle, sorry, a state with definite number of particles, a definite number of these phonons, the average of u in whatever point will be always zero, right? Intuitively, this is clear because you're in a state with a given number of particles is an oscillation with given energies, or everything oscillates and averages out. but there are, of course, the squares of displacement which are not zero. Good. Suppose we want to get a state where displacement is not zero, then we cannot just take a number state. We need to do something more complex. We need to make superpositions of the states with different number of particles, with different number of excitations. Good. That was about elastic string. And now can immediately jump to physical vacuum. Let's see how I'm doing. Time or pretty good. Pretty good. Let me say something which you know already. So, the quanta of electromagnetic field are called photons, right? So this is obtained by quantization of Maxwell equations in the same way. So first, the Maxwell equations are presented in the form of oscillators. They are quantized. So these particles are called photons. Good. Where they do live, where they're situated, was an index which labels all these particles. They live in the basis of all oscillator modes. And for electromagnetic field, there is an index which is composed from quantized momentum of a particle and control question. What is this? What is the second index which labeled all possible electromagnetic waves? Yes, very good, sir. It's polarization. So for any given K, we can have two polarizations. And for instance, one can choose linear polarizations. Both are perpendicular to the direction of this vector. Two possible polarization directions. Or, as we learn from optics, it can be in any superposition of the two. For instance, circular polarization when two linear polarizations are taken with the same weight. Right, so it's usual to represent superpositions with photons. Tell about superposition involving polarization of light. Good. So what labels the states of the fields? It's a number of photons in each of these multitude of the states. Fine. Let us again. Let me cite something which you almost certainly know about photons. The energies they come from this universal expression for the system of oscillators. The energies are just h bar omegas. What is omega for us? It's c times k, speed of light times wave vector. Momentum, to get the momentum, it's good to consider energy flow. And for that, we would express the Poynting vector in terms of number of particles that will allow us to find the value of potential. Good, we obtain that energy is just pure momentum. There's no no mass at rest for photons. That has this is a sound of relative of special relativity theory. What for statistics? Well, just per construction, these particles are bosons. One cannot make fermions from classical field. Well, fortunately or unfortunately. Fine. Some more information about phonons, which is less obvious. How about spin? In principle, all bosons should have spin. All bosons should have integer spin. The smallest integer spin, the phonons could have zero spin, but in this case, there is no number associated with polarization. Next possibility is that they have spin 1. But if you recall, spin 1 corresponds to triple degeneracy of the states. So there are states with projection plus, projection minus, and projection 0 on any axis. But we have only 2 polarizations. It's tricky business. So one can explain it as follows. These 2 polarizations, they do correspond to spin components. In this case, in any case, for any atom, there is always a natural quantization axis, which is the direction of its propagation. So 2 polarizations would correspond to different orientation of spin with respect to this axis. Then the natural question, where is this component? Yeah, how can I write it? Perhaps spin could be like this. That is not realized owing to the fact that photons, they always go with speed of light, which means that we are never in the system. We cannot rush as fast as photons. If we could, we could actually observe all 3 components of photon field. That would resolve this paradox. Third, that fact, phonons have spin 1, but only 2 possible polarizations because they always go with the speed of light. Right, one could say what's the coordinate of this particle. And well, again, for the same reasons, it's not a good idea to think of coordinate of a single photon. At least in linear optics, one can actually see beams of light, but it would be impossible to set coordinates along this beam in the direction of the beam propagation. So it's just not a good idea to ascribe any coordinate to a phonon. Or did I write four? No, there has to be photons, of course. We are talking about photons. Right, good. So we are a little bit patching relativistic theory. So let me also recall concepts of relativity. In classical limit, one can sort out relativistic fields into classes. Some of them has zero rest mass, and those in classical limits correspond to classical fields, like electromagnetic field. If rest mass is not zero, well, it's matter. It's particles with momentum and coordinate, electrons, protons, neutrons, whatever. Fine. I guess it's time for a break. All right, let's have a break till 9:40. So, ladies and gentlemen, I'm back. Let's go on with the lecture. So we understand the photons as particles. Most of them you have already known, but we now get it on a solid basis of the field quantization. Let me write field operators for electromagnetic wave, electromagnetic field. Again, we can make use of normal coordinates, which we have already computed classically. This normal coordinates can be easily converted to annihilation creation operators. And reverting this, we got expression for field operator. Remember, we didn't have scalar potential in our gauge, in Coulomb gauge. So we have only field operator for vector potential of electromagnetic field. Let's see it obeys the same structure. So what do we see here? First of all, if we look at a field in a given point, a given time, it is contributed by all modes with all possible polarizations and all possible momenta. Right. Each mode is represented by annihilation operator, and here in complex conjugated expression we have a creation operator. Good. So there is a plane wave factor associated with each mode. Yeah, I see the question. What else do we find? This is vector quantity. So we find the vector here. There is a vector, actual vector for each polarization. And all right, this ugly square root. Fine. Let me look at the question. What is HC term? This is as in many places of this course, just means Hermitian conjugated. So if I write whatever, anything, B plus HC, this means B plus B Hermitian conjugated. All right. Sir, please pay attention that this works on the on this operator. So, in fact, the vector of polarization also gets conjugated if it's complex. If it's a complex vector, it makes a difference. Good. So this is vector potential, and now we can get to actual field variables to observable fields. You recall that vector potential by itself is not an observable. We get to electric field and magnetic field. The question is how. What did I do to arrive to these relations? Starting from the formula for vector potential. Well, I just recall standard relations which we learned when talking about Maxwell equations. Magnetic field is actually the curl of vector potential. And the electric field, who remembers this? Yes, very good. Electric field, as we remember, is the time derivative. Nabla theta, sorry, it's not Nabla Nayan, it's gradient. Gradient of phi would also be at place, but again, we are still in Coulomb gauge, which in the absence of the charges presumes that scalar potential is zero. So it's only derivative of vector potential. We differentiate this expression with respect to time, with respect to coordinate, to arrive at the expressions for field, for electric and magnetic field. Very good. That was about field operators. Now we have everything for applications. And let me talk about the mysterious quantities. So I will talk about 0-point energy. Each oscillator has 1/2 of the quantum in its ground state. There is some energy in the ground state of oscillator, which is called 0-point energies. I will talk about uncertainties. So there is uncertainty, Heisenberg uncertainty. What was that? There are similar uncertainties for every field because again Any field is can be represented as an oscillator with generalized momentum, generalized coordinate. So there has to be similar uncertainties in the field. Right, and I talk about the fluctuations of the field in vacuum state, 0-point fluctuations. So in the ground state and vacuum, there are still fluctuations of electric and magnetic field or any field. Right, let me explain this fancy picture which I put along with these items. Many years ago, I've been kind of refreshing this course of advanced quantum mechanics, and I was surprised to discover that many items related to second quantization have been adequately explained at Wikipedia. Well, Wikipedia is, of course, very valuable resource. However, yes. However, if one gets, if one looks for a little bit structured information, like information in natural sciences, Wikipedia is usually marginal. At best, it doesn't contain explicit errors, but for most of questions related to physics, I found kind of structural errors. It looks at all these articles are written by students which are much younger than you, which don't get any whatever experience with things which they have, and just copy it from textbooks without much understanding. Fine. In contrast to this, the Wikipedia articles about second quantization have been written kind of at professional level. Not that they contained remarkable discoveries, but it was a pretty good outlining. So I got interested. I wanted to understand what is the source of these articles. And the series of these articles was really mysterious and very unusual for me. Tracing some insignificant references in this articles, I have figured out that in the United States, in California, somewhere near Pasadena, there is a private research institute with very good, very interesting mission. Namely, they wanted to utilize all these things which I listed, namely 0-point energy and vacuum fluctuations, to achieve interstellar travel. For instance, to get engines which can work without any fuel, just utilizing 0-point fluctuations. So apparently there was an institution, so I don't think the goal of this institution is real, but mine is real. And apparently there were some scientists employed, and they wrote these Wikipedia articles with a little bit of advertising of this institution. Fine, it was useful, and that's why I get this fancy picture. Let's look at it, and as a side exercise, let us understand if you can really fly using the 0-point energies. Good. First, what is this? It's simple. It comes from the Hamiltonian of oscillator. There is some energy in any oscillator, even without any particles, for electromagnetic field, without any photons. How to picture it? So there is a parabolic potential of the oscillator, and zero is here. But the ground state, well, the ground state owing to uncertainty is spread a little bit in x and momentum direction, which means that its energy is a little bit above zero. Fine, this is this 1/2. So each oscillator mode bears 0-point energy. Fine. There is this energy, and okay, let us first answer this question. Can we use this energy? I guess I have very good audience, sir. I address this question to you. Not to the scientists in Pasadena. Yes, kind of the form of the question suggests that you cannot. Who can explain why?
Well, I would think that you cannot really use energy. You need to go to a lower energy to use the energy. I don't think that's possible.
Yeah, right. It's ground state. But anyway, what the answer which I wanted that in general we can use energy only if we go from one state to another state. If we change something in the system, we could actually change the frequency of this oscillator to get this energy. But that's not possible, that we cannot change the frequencies of the uh, photons in vacuum without changing the vacuum. All right, sure. The answer is positive. We can use this 0-point energy, but only in case we can modify the properties of vacuum. Fine, very good. We cannot, we don't know how to, but let us at least make an estimation. Perhaps the energy is so small that it's not worth it, not worth an effort. Right, so let us compute this for electromagnetic field. How do I compute? I sum up all oscillators with 1/2 h omega bar. Yeah, it is usual trick which we play here. We replace summation over k by integration over k times volume. Right. So we need to integrate this. Omega k is ck, which means that this integral diverges. This integral diverges at dk. Right. Sure, one has to live with this and understand that eventually, yeah, here I just write it in terms of frequencies because I will integration in terms of frequencies instead of integration of k, because I will need it in the near future. But what we obtain is volume times infinity, so even energy density corresponding to this contribution is supposed to be infinite. Good to know. So although we cannot change it, as wealth of energy we can extract. There is a fundamental question, fundamental and very practical, because it concerns our survival. What is this? The energy in general relativity corresponds to a mass. Any energy accumulated to space would correspond to mass, at least per unit volume of this space. Right? But if we imagine ourselves in a universe which is full of mass, there will be gigantic gravitational potential, gigantic gravitational forces, infinite, and we have no chance to survive. These gravitational forces are not observed for obvious reasons, and the question is why zero-point energy does not contribute to gravitation. Right, so human conscious has resolved many questions about this word. This question is not resolved, although it looks fundamental, but still it's not resolved. Some ideas about this come from supersymmetry theory, which suggests that at some sufficiently high energies, we have the same amounts as strict correspondence between fermionic and bosonic particles. Each bosonic particle has a fermionic counterpart. And one can show that as far as zero-point energy is concerned, fermions add the same sign with minus. So in supersymmetry, at least there's no divergency at high energies for contribution to zero-point energy. But anyway, it remains finite, and in a very big universe, it would still result in tremendous gravitational forces. So there's no answer to this question. I'm sorry. From the other hand, well, why do we have to know this answer? Gravitational problems are rather far from us. Let's be happy that we still survive in this world. Let's go further. Let us see. I've mentioned that in order to utilize zero-point energy, we have to change vacuum. And talking about vacuum in general, it doesn't seem to be a realistic idea. However, I want you to understand and to know that we can change vacuum in a certain interval of energy. It's very simple. If you're talking about vacuum for photons, we could just use a medium, the electric medium, transparent, with some different um, um, dielectric constant, right? That will change vacuum. Why? Because it changes because it changes velocity, because it changes speed of light in the medium. So all quantization equations will remain the same. There will be the same oscillators. The only point that energy of these oscillators will be lower. So we can compare the results. We can compute this energy accumulated in 0-point fluctuations owing to this change of vacuum. Right. It is important to understand that we cannot change the electric constant at all energies, at all frequencies. We have to restrict ourselves to um, energies of the order of atomic um, constants. Right. With which we can do this estimation. So here we just take a difference of cubes of velocities and we integrated our frequency, but I will restrict integration by some frequency of the order of atomic energies. Right. That is how much will I get? For convenience, I presented, I introduced here atomic units. So I rewrite atomic energy in terms of Bohr radius. And Bohr radius, that's a stupid dielectric constant of vacuum. Anyway, it's all consistent. Right, so I can rewrite this estimation, the change of energy due to modified vacuum, divided by volume, and what will eventually take in atomic volume. Right, and what will I get? I get atomic energy with some coefficient. Let us look a little bit more detail at this coefficient that contains electronic charge, fundamental constant, speed of light, and this dielectric constant of vacuum, which always comes in System International with electronic charge. Right. This is first time we see a famous fine structure constant, which is a combination of fundamental constants characterizing how strong is interaction of matter and field, interaction of light and electronic matter in our world. This is dimension is constant, and as you see, it is small. It's like 10 to the minus 2. Good. What is our conclusion? The conclusion is that the 0-point energy, which is kind of in our gasp, at least you can feel the space with atoms and thereby modify um, photon oscillators. What is in our gas? We can we can change it. We can change 0-point energy, but the change will be pretty small in comparison with atomic energy. There's a factor of 10 to the minus 6. Right, that's what I wanted to say about 0-point energy. Any questions at this point? It doesn't seem to be the case. Let me just a little bit accelerate. I want to talk about uncertainty relations. And I want to get it in some general form. Again, in order not to recalculate it separately for any field which comes across. What's the basis for these uncertainty relations? It's the basis that momentum and coordinate do not commute. From this, according to Heisenberg, we have uncertainty relation. Sure, that's simple, which means that for any two apparatus, to characterize their uncertainty, we just need to compute their commutator, right? We are working with field operators, and we know that for any field, any operator is a linear combination, linear superposition of creation and annihilation operators. So I put just some coefficients in front of these creation and annihilation operators to represent any field operator, again, without specifying the field. I need two operators, and yeah, that's what I put here. Now the calculation, which is very simple. I need to compute the commutator of this two expressions. Right. I know that all A commutes with all all A commute with all A, all A dega, A dega commute with all A dega. Then and non-commutating terms can come with A and A dega. So I get it. I substitute it, I express it in this way. But I know that the commutator of A dega is just Kronecker delta function. That's why I get to this commutator for any field operators. The commutator by itself is not an operator. It is a number, like for coordinate and momentum. And having the expression for field operators, we can understand what kind of a number it is. Let me do the same for vacuum fluctuations. Wait, there was a question. How pi cube became pi squared in the denominator of the prefactor? Let's see. I guess it was several slides ago. Let me find it. Here. Who can explain this? So here we have pi cube. Here we have pi squared.
It's about the slide just before. Is the integration.
There's no integration.
Ah, okay.
All right. We don't have much time, sorry. Vacuum fluctuations. Vacuum fluctuations. And what do I have to do in order to compute vacuum fluctuations? I need to evaluate the average of two operators in the ground state, vacuum state, and right, so it's eventually a commutator of two operators. I can run very similar calculations. Now I want to express anti-commutator. Again, I start with a double sum, but since all these commutators sorry, those are anti-commutators. These anti-commutators for vacuum state are not zero only for equal K and L. So end up with this. Also a number which is expressed in terms of coefficients in front of annihilation operators in the expression for field operator. Well, in particular for the fluctuation of operator X, I found this. Then if we have quantized any field, we can immediately compute vacuum fluctuations. Fine. Let us get to concrete expressions. Right. Let's try what we have, what we already know. Let's look what kind of fun sensor we have. Let's take magnetic and electric field as an example. Right. We need expressions for field operators. We have them. So we apply the formula which we just derived. And that's what we got in K representation. So there is uncertainty between two components of the fields, magnetic and electric one. And after substitution and expressions, that's for field operator, that's what we got. It's a bit funny how to interpret this. Well, it has to be converted to the integral, and the integral can be converted to this fun expressions. It means that the fields do not commute in different points. But if they come to the same point, they commute very strongly. They do not commute very strongly. It's a derivative of delta function, right? Delta function, this is derivative with respect to that. Which is not good for any understanding. So it's something between 0 and infinity. Everything is between 0 and infinity. In order to make sense of it, let's have some averaging over space. So let us take our space. Let's make cells in this space with a size of delta L, right? And let's average magnetic and electric fields over the cells. Then it will correspond to the following. So the magnetic fields and electric fields do not commute in the neighboring cells. They do commute in different cells. They don't commute within the same cell. And the answer within the cell, it blows up if cell becomes smaller and smaller. It's manifestation of delta function. Sure, that is, if you have uncertainty in coordinates, the uncertainties of magnetic and electric field, they grow with this uncertainty. Fine. Let us compute fluctuations. It's again, I can use the expressions which we have obtained for general field. That's what I get. And again, it's in principle divergent expression, right? It contains summation over k, and each k gives at something. Right, so I could reduce it to integration over k, but integral will diverge, so I'd better cut it at some big k. I can count it on this space uncertainty which I just introduced. Fine. So the fluctuations of electric field are eventually of the same order of magnitude. In the same way, can compute fluctuation of magnetic field, again using the same formula, the same power law as I get for uncertainty. It all depends on space resolution. If you increase space resolution, you see more and more pronounced fluctuations of these fields. Right. Let us estimate these fluctuations. Just to entertain you at the end of this quantization. Right. Can we observe vacuum fluctuations? To accelerate it, I would say we cannot observe it directly, because if you look at vacuum, you just see empty space. What we can figure out is the correspondence between 0 point energy and vacuum fluctuations. So as you remember, there is energy density of electric field, and that get terms proportional to capacitive energy and inductive energy. So if there are any fluctuations, they also create this energy. And this energy is precisely the energy, 0-point energy accumulated in the oscillators. So there has to be a correspondence. So let us try to make an estimation. That's what we get at finite length scale. And inspired by a previous example, we can evaluate this fluctuation at atomic scale. Right, just substituting Bohr radius then it's a good idea to compare with this typical atomic field, electric field at the Bohr radius. We would expect something small, right? Those vacuum fluctuations, perhaps negligible, cannot be observed, but we got astonishingly big answer. In fact, electromagnetic field fluctuations at this space scale exceed average field in atoms by a factor of 100. Something goes wrong, something is not consistent in our world. Right, the if average field is smaller than fluctuations, then our atomic series is all wrong. So how to find why it is still consistent? Just to understand a little bit, to think more a little bit. This is the answer which you get for instant fluctuations. But it means that these fluctuations are contributed by all frequencies. And most fluctuations at this wave scale, they have a frequency which is much bigger than electron energies at this atomic scale. Right? These frequencies are computed from this uncertainty of space. I need to substitute Bohr radius here. And this is indeed about 100 times bigger than atomic energy. It means that most frequencies of this fluctuating field just do not affect anything about behavior of electrons. They're too fast. Efficient fluctuations are at much smaller frequencies. As we discussed, they have to be confined to atomic frequency. So, in fact, one needs to compute it at a different, estimate these fluctuations at very different length scale. And we found thus, one finds correspondence. The correspondence which we have already seen when we estimated 0-point energy. It must correspond, it does. The 0-point energy at atomic scale is somewhat 10⁻⁶ of the atomic energy itself. Very well. I also have a very short story about the single oscillator. Since I did it in previous lecture, I ought to make it quantum now. It's the same story. I need this generalized. I have already obtained this generalized coordinate, generalized momentum. I can now use it and eventually quantize the oscillator in question, deriving operators for the current and voltage through the oscillator. I can estimate 0-point energy, surface uncertainty relations. I can estimate vacuum fluctuations of charge of current through an oscillator of voltage fluctuations at the capacitor. You might want to check these formulas for realistic capacitors, realistic oscillator contours, for instance, in your mobile phone, and see how big these fluctuations are. With this, I conclude my lecture. We did a great job. We have quantized field, any field, in particular electromagnetic field. Most examples we have taken from electromagnetic field. We did some applications through other fancy applications, 0-point energy fluctuations, vacuum fluctuations, uncertainty relations. That's it. Thank you for your attention. I will stop the recording and then answer your questions.